Good afternoon, everybody. Welcome to session 15. Yeah.
All right. Well,
this session is going to be chaired by Dr. Brent Robinson. So now let me introduce Dr. Brent Robinson. Dr. Robinson is currently Vice President, Pile Dynamics USA. Dr. Brent leads the research and development efforts, trains clients, and lectures internationally on dynamic testing, integrity testing, and installation of verification of deep foundations. He earned his PhD in civil engineering from North Carolina State University and an active member of the Transportation Research Board, Deep Foundations Institute, and International Association of Foundation Drillers. So I welcome Dr. Brent Robinson to chair this session.
Thank you very much, Dr. Rao.
Yeah,
and
due to some sudden emergency, the co-chair could not make it. So I will assist Dr. Robinson in discharging his duties as co-chair. Okay, thank you.
Thank you very much, Dr. Rao, for stepping in on short notice. And it is again my honor to introduce our SOAP lecturer, Dr. Vinod. Dr. Vinod, if you'd like to start sharing your presentation, that would be a good start. While we go ahead and do that. Dr. Vinod is an associate professor at the University of Wollongong in Australia. 1 second, let me bring that back up. He received his doctoral degree in geotechnical engineering right here in Bengaluru at the Indian Institute of Science, and then worked as a research fellow there and at the University of Wollongong before joining as a lecturer at UOW. His research is focused, and he'll discuss with us today, on numerical modeling of granular material and soil dynamics, as well as earthquake engineering and ground improvement techniques for rails and mines. He is an associate editor of the Journal of Materials in Civil Engineering for I.I.Sc and a co-editor of the International Journal of Geotechnical Earthquake Engineering in the US. He's also actively involved on the Australian Research Council in the Cooperative Research Center projects on ground improvement techniques, railway geotechnics, and mine tailing. He's published over 85 peer-reviewed research papers in reputed international journals and conferences. And today he will discuss with us his work on numerical simulations of Coir Geotechnical or Geotextile reinforced soil under cyclic loading. And with that, Dr. Vinod, the floor is yours. Thank you very much.
Thank you very much. So thanks for that. And before starting my presentation today, I would like to acknowledge the organizing committee for giving this opportunity for presenting some of the preliminary work that we have carried out on the application of Coir Geotextiles for transport infrastructure development. Before going into the details of the presentation, let me give you some idea about where we are from. In Australia, we are here in New South Wales, and we are almost an hour drive basically south from Sydney. So that's where our main campus is located. So that's let me put some spotlight here. Yeah, so we are here south of Sydney, around an hour drive from Sydney Airport. And we do have campuses in Nowra, Batesman Bay and Bega for the south of New South Wales. Now, coming to this research that I am trying to highlight in this presentation today is basically a discussion that we have started with the Coir Board Government of India a few years back, along with Professor Beena from Cochin University of Science and Technology, to see whether we can use this Coir Geotextile as an eco-friendly material for low volume road constructions in rural areas. So when we were looking at and investigating literature in this phase, we could able to find a lot of work on monotonic loading of these materials and carefully looking at the interaction mechanism of soil and coir geotextiles, but we couldn't find much details of this material performance under a cyclic loading condition, especially under a heavy, fast-moving truck or a high-speed rails, how this material is going to perform. Now, as you all know, we have quite a recent push everywhere to look at more environmental friendly materials for infrastructure development. I believe the coir geotextile is one of the best material that we can think of for using and developing infrastructure constructions. With that short background, let me quickly introduce our co-authors, Abdullah, who has done this work as part of his master's thesis, who has carried out this preliminary computational model. I just have to put that preliminary word here because this model has to be extended with some of the key features basically shown by coir geotextiles, which I'm going to highlight in a later part of my presentation. And we do have collaborators from University of Leeds and I.I.T, who will be looking after the experimental part, looking at more towards interfacial friction during cyclic loading and microchemical analysis in detail. And we have Professor Bina from Cochin University looking some of the details under the monotonic loading condition to help with this research. All right, with that, let's move on to the basic introduction as the problems associated with soft soils. And I'm sure there is no introduction required for this. And you all know that for a soft soils, it's always is associated with low bearing capacity, and you have high compressible material there. You can have very high consolidation settlements sometimes happening, and you have low permeabilities. And because of all these key properties, you can have failures happening onto the subgrade soils under different conditions. It can be from a truck loading, or it can be due to the drainage problem. So it creates a lot of infrastructure problems for practicing engineers. And you can see some of the key photos which shows how it majorly affects some of the major artery roads connecting to the main roads in these cases, which can affect the traffic a lot. So as a practicing engineer, if you face problems on soft soils, soft subgrade soils, what we generally go with is look at improving the soil strength by dewatering. And if you look at dewatering, we have a lot of technologies developed in hand. We have preloading, which is a pretty old technique, preload surcharge, or using you can see using the vertical drain. So you can see if you have a soft subgrade, you can use a preload and you can create additional drainage using vertical drains, and you can accelerate the consolidation process. So we already have established quite well information on how to improve the soft strength using these kind of techniques. Now, on the other hand, we do have materials. For example, if you look at the synthetic geogrids perspective, we do have geotextiles, geogrids, and geomembranes, which can basically provide a strength towards these materials, and which provides additional reinforcement effect for these subgrade for these subballast or sub-base materials. So you can see a couple of photos which I have shown here, where the geogrids have been used between the interface between the subgrade and the sub-base layer, which basically act as a reinforcement mechanism. And here you can see a combination of geogrid and geotextiles, which basically act as a reinforcement plus and a dewatering technique. So you can see a combination of both has been applied here to mitigate, for example, an effect of mud pumping in case of a railway track. So if you have a geotextiles here, it will try to dissipate that excess water pressure, which is developed due to the cyclic loading coming from a truck or a fast-moving vehicle, can be dissipated through these geotextiles, and the geogrids can provide an additional confinement effect through the interfacial friction developed between the soil and the geogrid. So we are pretty much very much comfortable in applying or using this material for various infrastructure development. Now, the challenge or the key issues that we need to look at carefully here is during the maintenance period. Now, when it comes to the maintenance, especially in terms of railway, what basically happens is we have the machine which is running onto the railway track, and they basically pull the track, lift the track up, and compact the ballast into the track. So during the whole this process, what happens, what practicing engineers often observed is these geogrids got caught into this machine and becomes a very big issue for during the maintenance time. We do have observed some cases reported where this geogrid has to be completely removed for the realignments of the road, and in turn what happens, it becomes an additional waste as part of all these construction process. And as you all know, we are going towards more green kind of approach, and we are creating on the other side, we can see the waste from this material is creating additional plastic waste, which we would like to reduce as much as possible. And looking in that perspective, the application of natural materials like Coir Geotextiles and like example jute gives very promising prospects that it won't create any kind of natural waste materials and thus a low carbon footprint. Now, coming to the Coir Geotextiles, which I'm a bit interested today to look at and showcase some of the preliminary findings that we have from the numerical modeling. So those who are new to this, as you can see, Coir Geotextiles is basically a thin, flexible, permeable sheet made of coconut fibers, and that enhances the mechanical behavior of soil. And as I have mentioned earlier, we do have a lot of work carried out in this area for the last 2 decades to look at the improvement in the soil stability. For example, if you are looking at the slope stability, we have used Coir Geotextiles pretty comfortably in controlling the movement or the instabilities of the soil slopes. The advantage of having these kind of natural material is, according to me, which needs to be, this mechanism needs to be strengthened. It acts like two cases. One, in a short-term perspective, this material will behave exactly like a synthetic material, which provides a reinforcement effect. And in a long-term perspective, what happens is, due to the biodegradable nature of this material can leach lignin into the soil, which leads to a kind of a chemical stabilization later on onto the soil. So we have observed this kind of mechanism, but we need to understand a bit more into this mechanism and come out with a model which can be used comfortably by a practicing engineer to predict this behavior for short-term and the long-term perspective. Now, it improves the soil stability. Sorry. It improves the lateral resistance and increases the bearing capacity. And this has been reported widely by various researchers. So if you look at the geotextile materials, you can see we have PVC, polyester, and polypropylene and polyethylene. And on the natural side, we have coir, jute, bamboo, and palm. And you can see that coir and jute has been widely used for various construction. For example, the recent study that we have carried out at University of Wollongong is the application of jute drains compared to the wig drains, and how the performance of jute drains are compared to the wig drains. So it's quite interesting to look at how these natural materials perform in real practice. Again, we need to address a lot of challenges associated with the degradation of these materials for a long-term perspective. I'll quickly show you some quick photograph of the woven and non-woven geotextiles that we can have for different construction process. In this study, we look at more on the woven geotextiles for our numerical modeling. Coir fibers, as I highlighted, coir fibers are basically from the coconut husk, which is an external peel of the matured coconut. So that's how it has been prepared. And you can see that the chemical composition clearly shows that a high percentage of lignin content associated with these coir fibers. So that has a positive effect on the degradation of the coir fibers plus the stabilization of this material in a long-term perspective. In short, you can see coir geotextiles we can have desirable engineering properties for these materials. It's eco-friendly, there is no doubt about it. And you can see the biodegradable nature of the coir geotextiles. And if I expand a bit on biodegradability, we can see that it has both advantages and limitations. So the major advantage is that you can see that it biodegrades, and in few years' time, the material disappears. And if the infrastructure we are looking at is only for a short-term perspective, we will get the maximum benefit out of this material in that time period, and then it completely degrades into that material. And if you are looking at an infrastructure, transport infrastructure condition, you can just mix the material up, and it becomes a kind of a fiber reinforced soil, which further enhances the properties of the subgrade material. So that's the advantage of it. And the limitation, as you know, it's whether we need to apply this material for a long-term condition or a short-term condition. That's where we need to draw a fine line. And that's where it is highly important to develop a biodegradable model to predict the applicability of this material for infrastructure development. So that is actually our ultimate goal in this research. So to come out with a computational model which helps the practicing engineers to design these structures, infrastructure for the years that they are going to design the infrastructure on. Right. With that broad aim in hand, we look at this material in terms of functions. You can see that the major function is exactly same as that of the geosynthetic material, like reinforcement. It acts as a reinforcement, it acts as separation, it has filtration, it can be used as drainage. Now you can see it's also performs exactly similar to the geosynthetic material. So only thing is that the biodegradability of the material needs to be considered in all these approaches. Some of the field application you can see here, it doesn't stop us in applying these materials to infrastructure. So you can see people have tried in using this material for low volume roads. That's road construction using coir geotextiles, slope stabilization using coir geotextiles. So we are trying to use these materials for different infrastructure construction, but we need to understand a bit more from the very fundamentals how this can be designed in the first place for long-term and short-term stability point of view. With that, let me quickly show you some work already being carried out experimentally on the bearing capacity or the load settlement behavior of this material. So you can see that which has been reported here. You can see that's a typical load settlement behavior of a unreinforced soil. You can see that's the applied pressure versus settlements. You can see that is basically for a unreinforced material, and you can see if you are reinforced with different coir geotextiles, you can see there is an increase in the applied pressure. So you can see the bearing pressure increases with the inclusion of your coir geotextile. So it clearly shows an increase in stiffness and an increase in the applied pressure or failure pressure with the application of coir geotextiles. Now, this is another experimental study carried out to look at the bearing pressure and the settlement for different reinforcements of coir geotextiles placed at different depths. So similarly, you can see here that's non-reinforced sand, and if you reinforced with different coir geotextiles, you can see there is an increase in the applied bearing pressure. So you can see there is a slight increase in the stiffness plus an increase in the ultimate bearing pressure too with the inclusion of coir geotextiles. So basically what it shows here is with the inclusion of geotextiles, coir geotextiles, we can get an increase in stiffness and an increase in the bearing pressure with the inclusion of coir geotextiles. Now, this is some information about the geotextiles that they have used for this experimental work. Now, when it comes to the cyclic load, we could only find very, very few work on coir geotextiles. What I'm showing here is the work on geosynthetics. So you can see what I'm trying to show you here is how the settlement responds with and without reinforcement under the cyclic loading. So you can see here that is without reinforcement and that is with reinforcement. So how the settlement is controlled for different subgrade conditions using with and without reinforcement under cyclic loading. Now that's where the challenge we have. We could rarely find literature on the cyclic loading of coir geotextiles reinforced soil. Therefore, we are carrying out at our university a detailed large-scale testing on the cyclic loading of coir geotextile reinforced soil so that we can validate these models before applying to design any kind of transport infrastructure. Right, the degradation of the coir geotextiles. There is one study reported here how the reduction in the tensile strength is happening with time. So you can see that's a reduction in the tensile strength of untreated and the treated coir geotextiles. So that's some of the study which has been done to look at the degradation what we have observed on the onto these coir fibers. So with that, let's move on to the numerical work that we have carried out. So I divided that into part A and part B, where we look at in the first part very quickly into the monotonic loading, which we has carried out basically to calibrate the model. And we have three different conditions here to look at. The first one is the unreinforced, where we have a layer 1 we consider as a sub base and layer 2 as a subgrade. And you can see layer in B, in the second condition, we have a coir geotextiles going at the middle of the sub base layer. And you can see here in the third condition, we put it at the interface between layer 1 and layer 2. So these are the three configurations that we have looked at in our model. And our model we have which is a size of 500 by 800, which is basically similar to one of the literature which shows the load settlement behavior under monotonic loading. The material properties are pretty much same. We have looked at the well-graded gravel. We have looked at and we have placed reinforcement at the interface and at the middle of this subbase on the layer 1. And the reinforcement we have considered as a plate element, and we have used a linear elastic model. And for the soil, we have gone for a hardening soil model with hardening soil model here with small strain stiffness, so that we can capture the variation of the modulus with respect to the shear strain, which is critical for the dynamic analysis. The soil properties, I'm not going into the details of the soil properties here. So that's various soil properties we have adopted based on the work reported by Subaida in 2016 in one of the laboratory experimental work on coir geotextile reinforced soils. So after that, we compared and calibrated our model with the experimental data. And you can see that's unreinforced bearing pressure versus settlement response from this finite element model compared to the laboratory work reported by Subaida, and that's reinforcement at the middle and at the interface. So you can see here that's our model has captured the results very similar to the laboratory experiments. And you can see here at the interface, as expected, has shown a very high bearing pressure compared to the other reinforcement placed at the middle of the layer 1. We have plotted that in terms of N gamma here, nothing surprising. You can see the N gamma increases with the settlements and reaches a constant value at large values of settlement. So you can see that's a variation here for unreinforced, reinforced at the middle and at the interface. We looked at different layers of reinforcement, whether to see whether the number of layers can influence the bearing capacity. And we have observed that it's increasing the number of layers has an insignificant influence on the increase in the bearing pressure. So you can see anything greater than 2 has not contributed much on to the increase in the bearing capacity. So, so you can see that there is an optimum value that we need to look at when it comes to the designing inclusion of geotextiles into the infrastructure construction. We looked at the friction angle, how the friction angle is going to affect the bearing pressure. So you can see with increasing the friction angle, the N gamma increases. As expected, similar trend has been observed for the reinforcement at the middle and at the interface. So there is no surprising results here with increase in friction angle. We have observed an increase in the value of N gamma. And similarly, you can see an increase in the modulus that for the subgrade have also shown an increase in the value of N gamma for the reinforced material, unreinforced, reinforced at the middle, and the reinforced at the interface. So these are all results highlights that these simulation, our model is able to capture the response very, very similar to the laboratory investigation. Looking a bit more closely into what's really happening inside the sample. So you can see how the stress distribution happening here. So you can see that's a stress for an unreinforced soil. And you can see with the reinforcement at the middle, we could able to reduce a bit. But with the interface, you can see we could able to control the pressure very carefully in this by reinforcing at the interface of subgrade and the subbase layer, or layer 1 and layer 2. Looking at the axial force developed along the reinforcement, so you can see a more distributed axial force developed at the interface when the Coir Geotextile is placed to the interface between layer 1 and 2 compared to the reinforcement at the middle of the layer 1. And you can see a very high axial force developed here compared to the axial force which has been reported, which has been shown at the middle of the reinforcement, middle of the layer 1. So you can see that's a more uniform type distribution, which has been very consistent and very similar to what reported by Kurian in 1997 on the variation of axial force along the reinforcement layer. All right, with that, I have only 5 minutes here. With that, let's quickly move on to the cyclic loading of Coir Geotextiles reinforced soil. We had gone through a bit of a challenge here without experimental data, how we are going to model the Coir Geotextile reinforced materials under a finite element or in Plaxis software. Luckily, we could able to find one literature by Sridhar and Kumar looking at the cyclic loading of a Coir Geotextile reinforced soil in a fully immersed sand condition. So we picked up that to calibrate our numerical model. So you can see that we have simulated a different condition very similar to what the laboratory experiment work has been reported by Sridhar and Kumar, and we have tried to capture with our model to see whether we can capture the variation of settlements with number of cycles very similar to what they have predicted in their paper in 2018. The challenge here is to to develop a cyclic input for in Plaxis software to capture this behavior. So that was one of our key challenge in modeling or extending this model to capture the behavior under cyclic loading. So you can see that with the new input that we have created in Plaxis, subroutine developed in Plaxis, we could able to capture the settlements versus number of cycles, very similar to what has been reported by Sridhar and Kumar under cyclic loading condition for a cyclic stress of 100 kPa and with a frequency of 0.5 Hertz. It's a very, very small frequency for a traffic condition. We then extended that model very similar to the layer 1 with 2-layer system, which we have calibrated in the monotonic condition to look at the effect of the amplitude of a cyclic stress and frequency on the performance of the Coir Geotextile reinforced soil. So we have used the same kind of amplitude here, and you can see the response of the model under different amplitude of cyclic stress. So you can see with the increase in the cyclic stress, we can see the settlement increases with the number of cycles. So we can see that we run this program up to 10,000 cycles, which possibly take around 3 days, close to 3 days to run this simulation under these kind of grid conditions. So you can see that's for the reinforced at the interface and at the middle. So you can see that if you look at the table carefully, you can see the reinforcement at the middle has shown a very high performance compared to the reinforcement at the interface. So slightly different behavior that we have observed compared to the monotonic loading in this case. Now, we have looked at the effect of frequency like 0.5 Hertz, 1 Hertz, and 1.5 Hertz. I still tell you that's a very small frequency when we are looking for a transport condition. But still, it captures the behavior of frequency under different conditions like unreinforced, reinforced at the interface, and reinforced at the middle of the layer 1. And similarly, you can see here the performance is slightly better when the Coir Geotextiles reinforced is at the middle compared to the interface under the cyclic loading condition. Now we looked at that. What's really happening here? We have kept everything same, exactly similar to the monotonic loading condition, but we have observed a slightly different behavior compared to the monotonic condition. And then we looked at very closely into the axial stress developed on the Coir Geotextiles, and we have observed that a very high magnitude of axial stress has been, or axial force has been developed when the Coir Geotextiles is very at the mid of the layer 1 compared to the interface. That probably due to the kind of load application that we have used under both static and monotonic and the cyclic loading, where in the monotonic loading condition, we have used a strain controlled approach, and here is a load controlled approach. So we can see there is a significant difference when the application of the reinforcement due to the application of the load or the type of loading that we are trying to do. Further, we need further experimental evidence to highlight the findings that we have observed here. That is currently in progress. So with that, let me quickly conclude that this numerical model, the preliminary numerical model, captures the soil bearing pressure versus settlement behavior, very similar to the laboratory experiments reported by Subaida and Sridhar and Kumar for both monotonic and the cyclic loading. Coir Geotextiles were installed at the interface between layer 1 and 2 and in the middle of the layer, and placing the Coir Geotextiles at the interface have led to the optimum performance under monotonic loading. There is no surprise. A lot of work has been carried out, and basically this is, strengthens their findings in the application of the Coir Geotextiles. Now, the number of layers, I have already highlighted that number of layers has shown an insignificant influence for n greater than 2. The application of Coir Geotextiles between layer 1 and 2 reduces the settlement around 38%. So I indirectly calculated the reduction in the settlement for synthetic, which is very, very close for a short-term perspective. So this material can behave very close to the synthetic materials in that the time frame that we are looking for. So the performance is quite good. We didn't have a direct comparison, but an indirect comparison shows that it can perform very similar to the synthetic materials. So the inclusion of Coir Geotextiles in the middle of the layer yielded the best performance under cyclic loading condition. And please note that it's considering the cyclic stress that we have considered in this investigation, which requires further validation using further large-scale experimental test data. The settlement was found to be increasing in cyclic loads and the frequency. The interface friction between the soil and the Coir geotextiles generates an interface shear strength and an axial force in the geotextiles that basically contributes towards the increased bearing capacity and reduction in the settlements. Limitation, I need to be very careful about the limitation of application of these Coir geotextiles for different infrastructure construction. First thing is that the coir fiber degradation and its effects on the response of reinforced soil. So it is very critical that we develop a model which captures the degradation of the coir fiber, and that needs to be integrated into any model to capture the short-term and the long-term perspective. So if we can able to predict the time frame up to which this material is going to perform, and that is exactly what a practicing engineer will be looking for before applying this or a wide application of this for any infrastructure development. Effect of different sub-base and subgrade material, including stress rotation during traffic loading, needs to be investigated. High frequency, we have only looked at around 1.5 hertz, which is very small for a traffic condition. And we need to look at a very high frequency and very high cyclic stress amplitude before applying this to any kind of payment infrastructure. And finally, we need a large-scale validation of the model with detailed large-scale and field investigation, which needs to be done before applying this to any field application. With that, I would like to acknowledge Coir Board, Government of India, Faculty of Engineering and Information Sciences for funding this research project, Australia India EMCR Fellowship from the Australian Academy of Science. I would like to thank Mr. Radhakrishnan and Dr. Ananda, Director of the Coir Board, former Director of the Coir Board, for providing financial support and Coir Geotextiles for this research, Professor Bina from Cochin University, and the computational and laboratory facilities at University of Hong Kong. Thank you very much. I think I exceeded a few minutes. I'm happy to take questions from the audience. Thank you very much.
Thank you very much, Dr. Vinod. It was an interesting presentation of your preliminary efforts, and we look forward to seeing some of that go final in the coming years. A question from the Q&A part of the chat. Harsha is asking, in general, the tensile strength is the predominant property of geotextiles. And also, we are concerned with the horizontal and vertical elastic modulus of the geotextile and how they are different in their direction of loading. And so how do you manage that behavior with a plate element and a linear elastic model?
Thanks, Harsha, for that question. It's a very interesting question. In this model, unfortunately, we did not look very closely into the modulus at different directions, like horizontal and elastic modulus. We didn't look at in that perspective. Since we have used only a plate element with linear elastic, we are majorly looking at the axial stresses that has been developed onto that reinforcement element. So I truly value your question. I think something which probably we have to look at in future in calibrating the plate element with more experimental data, and see whether we can capture the best element, for example, for capturing the deformation behavior or the axial stresses developing onto these Coir geotextiles. I'm not sure whether I answered your question, but I don't have a direct answer for that question because we didn't conduct work in that area. Thank you.
Thank you, Dr. Vinod. One question from me. Are you how much of the difference do you think that you're seeing in the laboratory studies is an effect of the reinforcement aspects of the Coir Geotextile versus any separation or filtration effects? Are these the grid style Coir, or are these that you're modeling, or are these more of a textile that would provide more filtration and separation to prevent migration of the fines from the clays up into the gravels?
Currently, we are looking at kind of even, it's a kind of geogrid type where we have aperture size, different aperture size. We are looking only one particular type of aperture at this point of time to see whether this can perform well for that type of subgrade materials that we are looking for. As I have told you, very few work has been conducted in this area, even to look at, for example, the effect of aperture size on looking at the reinforcement effect, or even the filter or the separation effect of this material. So in this study, what we have done, we, as I have clearly highlighted as a plate element in a 2D phase, we cannot capture all those aperture effect into the model. So it's we have not gone to that area. This is just a beginning to look into a more realistic goal in the future to see whether we can come out with a robust model to capture some of these key factors.
Well, very good. As you said, I think that we need to move on to our paper presentations. Again, Dr. Vinod, thank you very much for your presentation and your time. And we will look forward to future results on this subject.
Thank you very much.
Can I have one question, please?
Yes, go ahead,
Sure.
Dr. Rao.
Yeah. So thank you, Professor Vinod. Very interesting presentation. But there is a serious limitation comparing to synthetic material, because coir has certain limited lifetime. Even all the laboratory testing results are applicable only at the time of installation, but with the time they degrade. So there is serious limitation about that. And whenever this degradation takes place, the changes we are expecting should be improved before the degradation takes place. So as of now, they are using right now only for the slopes, where if you plant some grass or something, that grass will grow and induce the properties which we require by the time this degrades. But I am not sure how it is going to help in terms of improving the bearing capacity and all, because it will start degrading in certain amount of time. And regarding one more, where you have shown by increasing the number of layers, there is no improvement. You have shown one plot. There, my concern is that you have increased the number of layers beyond the pressure bulb. So obviously they will not have any effect. But conventionally, if you see the number of layers effect and all, if they are within the influence zone, then they may have some improvement. That's only my one comment. Thank you.
Yeah. Can I answer the first
Please,
point?
please.
Yeah. Thank you for that question. It's a very interesting question. I completely agree with you. That basically stops the application of Coir Geotextiles for different infrastructure construction. So basically the biodegradability has advantages and limitations. But what we are looking at here is there are a lot of practical application on the other side where we can use this material. For example, mine haul roads. It's only a temporary infrastructure that we require during the construction of the mine. So there are a lot of other, for example, low volume roads which connects to the main artery roads. So there are a lot of areas that where we can focus on in application of this material, and we can see that once the mine is closed, they don't want the plastic to be inside. So they want something which is natural, which degrades quickly. So I can see there are potentially a lot of application in the future where this material can be used for various infrastructure construction. And as you said it rightly, we have used this for slope stability, and I'm very much aware of that work has been carried out on the slope stabilization. There are two things which we didn't understand very carefully. One is the effect of these Coir Geotextiles in stabilizing the lateral movement using the reinforcement condition, and second is the leaching effect of the lignin into the soil. And this has a chemical binding which provides the soil. So we didn't investigate this mechanism very, very carefully, how this effect of leaching the lignin into the soil affects the chemical stabilization effect. So there are several mechanisms which is underlying to this material, and I think we need to do a careful investigation to make sure that we get the correct knowledge around this material so that we can apply to the practicing engineers later on. And that this is a humble effort towards that major goal. Thank you.
Well, thank you very much, Dr. Vinod. I wish we could talk more about the biodegradability. Maybe we can take that offline.
Thank you.
But we do need to move on. If you want to stay towards the end, if we have some time, we can maybe circle back and ask some more questions.